Hello, welcome to my talk all about fruit. This talk is on a comparison of using the fluid element method and the Reynolds transport theorem for deriving Navier-Stokes equation, and we will talk how we can derive Navier-Stokes equation correctly. The conventional methods for deriving Navier-Stokes equation include the fluid element method and using the Reynolds transport theorem. The fluid element method directly works on a small fluid element, such as the cube in the figure. Based on the conservation law, we can build the dynamic equation for the fluid element in a very intuitive manner, but the substantial derivative must be used, since the physical parameter f would be a function of the independent special variables x, y, and z, and time t. This derivation is very straightforward with the obvious physics, but the substantial derivative can be a problem in the compressible flows. The Reynolds transport theorem works on the whole fluid domain, examines the overall behavior of the fluid. In the derivation, the control volume, Cv, is used. Thus, the volume integral form of the physical parameter f, that is, the quality of this physical parameter, would be a function of time only. As such, the substantial derivative can be avoided. Using the conservation laws and the Reynolds transport theorem, the Navier-Stokes equation can be easily derived. Well, the understanding of the Reynolds transport theorem would be very important. In both derivation methods, two types of the force must be considered. The body force, which is generally proportional to the fluid volume. For instance, the gravitational force per unit volume, rho g, and the surface force is the force of the surface integral of the stresses. The stresses due to the fluid pressure, fluid viscous stresses, and fluid compressibility. In the fluid element method, the derivation is made directly on the physical parameter f. In the Eulerian representation, the physical parameter f would be the function of the independent special variables x, y, and z, and time. Thus, its time rate of change is generally given in form of the substantial derivative based on the rule of calculus. So we have the derivative f with regard to time given by this, and use the velocity component. We have this and this. Here we can see the expression as this. It is the conventional form for the substantial derivative. Reynolds transport theorem works on the quality of the physical parameter, the volume integral of the physical parameter f, the quality I. As a result of the volume integral, the quality of the physical parameter is the function of time only. It is independent of the special variables x, y, and z. As such, the time rate of change of the physical quality would be same as the normal derivative. So, no substantial derivative is needed, and the Reynolds transport theorem calculates the time rate of the change of the physical quality and given in this form. How to derive the Reynolds transport theorem can be found in my talk, Reynolds transport theorem. In the next few slides, the continuity equation will be derived using both fluid element method and the Reynolds transport theorem. These two methods are used to show the difference between these two methods. Many own that the different ways can be used to derive the continuity equation. Here, the fluid element method is used for deriving the continuity equation. Consider a cube. It is the fluid element. For a time interval delta t, the fluid mass in y direction flows in the cube from the vertical surface delta sy at the left-hand side. And at the same time, the fluid mass flows out of the cube from the vertical surface delta sy at the right-hand side. Therefore, the net mass increment is the difference between the mass flow in less the mass flow out. Thus, the mass increment can be calculated as this in y direction. In a similar manner, we can calculate the mass in x direction given as this, and in z direction given as this. So if we put all this mass increment together, so the total mass change is given as this. At the same time, since the volume of the fluid element is fixed, delta V given by delta x times delta y times delta z, so the mass is given by this formula. Its increment would also cause the change of density as this. So put this two mass increment together, we have the equation as this. And we can write the equation as this. Here, we must note the density differentiation with regard to time is given by a partial differentiation. It is because the density change here is due to the mass increment within the time interval delta t only. So we can write this equation in a vector form as this. This is the continuity equation. We can also use the Reynolds transport theorem to derive the continuity equation by simply taking the physical parameter f as the fluid density. It can be seen that the volume integral of the fluid density is actually the total mass of the fluid. In the control volume, the total mass is unchangeable. Thus, the time rate of the fluid mass must be zero given as this. Applying the Reynolds transport theorem in a form of this, we can obtain the integral form of the continuity equation as this part. From this integral form of continuity equation, we can easily deduce the differential form of continuity equation given as this. This is exactly the same as that continuity equation from the fluid element method. In the next few slides, the moment equation will be derived using the fluid element method and the Reynolds transport theorem, respectively. And we will see, in deriving the Navier-Stokes equation, we must use the substantial derivative carefully. In this slide, following Stokes, the total stress tensor is given as capital T double arrow. This is a combination of the stress from the pressure and the compressibility contributions. And here the second viscous coefficient lambda given by this coefficient. And the viscous stress tensor, it's an asymmetric stress tensor. It is derived directly from the fluid motion, rather than the conventional artificial construction of the symmetric stress tensor. If you would like to see more information about this asymmetric stress tensor, please see my talk. Is Navier-Stokes equation correct? Using the summation expression for the divergence of the viscous stress tensor and the definition of the stress tensor component, we can have this, and we can obtain the expression as this. Write it back to the vector form. It is as this. So we can obtain the divergence of the total stress tensor given as in this form. This is a very useful equation. We will use this in both derivation methods. So on the vertical surface at the left hand and the right hand side, the net surface forces in y direction is given and calculated as this due to the total stress tensor component T22, and here delta V for the fluid element is given as delta X times delta Y times delta Z. Similarly, for the stress tensor component T23, we can obtain the net force in y direction for the stress tensor component T23. And we can also calculate the net force in y direction due to the tensor component T21. So we put all this surface force together, we get the net surface force in y direction as this. Now for the dynamics of the motion of the fluid element, the Cauchy's momentum equation is used. It should be noted this is different from the actual Newton's second law of motion, but it is called Newton's second law of motion in many textbooks, since it can be superficially derived from this equation. This part is MAY, and this part is the body force on the element, and this is the surface force on the element. However, we must remember, in this case, for the fluid element, the mass is not constant if the flow is compressible. Now use the substantial derivative. We can write this equation further into this form. Similarly, we can derive the moment equations on x and z directions as this. Now put this together and apply the second viscous coefficient. We can obtain the moment equation in vector form as this. Here we can see the substantial derivative of the fluid acceleration given as this. And this part is the divergence of the total stress tensor, T double arrow. For the moment equation based on the Reynolds transport theorem, it is based on the Newton's second law of motion. The time rate of the change of the total moment equals to the total body force and the total surface force together. Here we can see the time rate of change of the total moment. This is the total body force and this is the total surface force. Why we can use the Newton's second law of motion directly here? It is because the overall quality, i.e. the total moment, is the function of time only. This is very different from the individual physical parameter f, which is basically a function of the spatial variables x, y, z, and the time t. So we can use the Gauss divergence theorem to change the total surface force into a volume integral as this. And then we can apply the Reynolds transport theorem. So we have the integral moment equation for the fluid as this. And from this, we can easily derive the differential moment equation for the fluid. Again, the expression for the divergence of the total stress tensor has been applied. Now, we can make some more mathematical manipulations on the moment equation from the Reynolds transport theorem. The vector form of the left-hand side can be written in Einstein's summation as this, and use the rule of calculus. You can write the terms as this. So the first two terms from the first partial differentiation, and the last two terms are coming from the second partial differentiation. The other terms, we can obtain the expression as this. Now, we write these terms back into the vector form. We have the expression as this. And we can see this part vanishes automatically due to the continuity equation. So the left-hand side of the moment equation is given by this. So we can obtain equation as this. So this is exactly the same moment equation as that from the fluid element method. Now in this slide, a discussion would be made for what is wrong when using the Newton's second law of motion directly on the fluid element. We know, in spite of the different form in original Newton's second law of motion, it is for the constant mass of the body. The universal Newton's second law of motion should be the time rate of the change of the momentum equals to the force applied on the body. So, in real form, the Newton's second law of motion should be given as this. This term is the time rate of change of the moment for the fluid element. And this term is the body force acting on the fluid element. And this part is the surface force acting on the element. So we cancel out the constant value delta V. We have the differential equation as this. And similarly, we can have the moment equation in x direction and z direction. As such, if we put all this together, we have the moment equation as this. So we use the definition of the substantial derivative. The moment equation can be written as this. And then the ordered terms in the left-hand side, we have the equation as this. If we compare this moment equation with the correct moment equation we derived before, we can see the x term here, and this term would be 0 if the incompressible flows are considered. That means if the Newton's second law of motion is applied directly on the fluid element, the moment equation would be not correct for the compressible flow. This is a big question for this term. In this slide, we will try to make some explanation on why we cannot use the Newton's second law of motion directly on the fluid element. Howard Banana explained the correctness of Navier-Stokes equation for compressible flows in his papers in 2005, titled Navier-Stokes Revisited, and in 2012, titled Beyond Navier-Stokes. He gave the definition of the substantial derivative as this. Here, the vector Vm is the Eulerian mass transport velocity. And for the fluid motion, we should have two different velocity. Vector Vm, the mass velocity, and the vector Vv, the volume velocity. According to the book, The Navier-Stokes Problem in the 21st Century, P.G. Marie said, for to explain the concept, one must distinguish the Euler mass transportation velocity Vm and the Lagrange fluid particle velocity vector Vv in the compressible flow. In the definition, the moment equation should be given as this. Here, we can see the fluid volume velocity vector Vv is used as the representation of the fluid velocity. But in the substantial derivative, the velocity here is different. It is the mass velocity. And a formula is given the difference between these two velocities as this. Obviously, if the flow is incompressible, and these two velocity would be same, but they are different incompressible flows.